Well, Project 2 is quite different from Project 1. Project 1 was data decomposition, that is, taking advantage of parallelism in order to speed up some computation by breaking it into smaller pieces, and now the smaller pieces can run faster. This is functional decomposition, in which we break up a problem by, well, what the different pieces need to do. We're not doing this for performance. Okay, understand, functional decomposition doesn't have anything to do with performance. It has to do with ease of programming. And so in this simulation you're going to create, you have temperature, you have precipitation, you have deer, and you have grain. And you're going to have some quantity of your own. We'll get to that. Okay, so the grain grows, and the grain grows depending on temperature and precipitation. The deer eat the grain. How much they eat the grain depends on the number of deer. If there's not enough grain there to support the deer, deer wander off. This is very much like Sim Park. If you've played Sim Park as a kid, or if you're still playing it, this is very much like Sim Park, okay? But functional decomposition is interesting to us in this class because of the ease of programming. That is, yes, you could ball everything together, but what we're going to do is we're going to isolate just the deer. There will be a function that deals just with the deer. The deer function looks around at the environment, the amount of grain, and so on, and decides what the deer population is going to do in the next month. There's going to be a single grain function. And the grain function is going to look around at the whole environment and decide what it does in the next month. If there's a lot of deer, it's going to go down. If there's no deer, it's going to go up. Depending on the temperature and precipitation, well, those control how fast it grows. And so this is a big advantage to doing multi-threaded parallelism, is because you can write these little miniature functions and that only deal with one quantity. Okay, so remember that. Each function only deals with one quantity. All right, let's look at the handout. So, yes, you're going to create a month-by-month simulation. It's going to go for 6 years. So it's going to go 2024 through 2029. Months are 0 to 11. And so you're going to decide what each quantity does for the next month and do that 72 times. You've got a current state, and this is your current state. Okay, inches of rain per month, and that's going to change depending on the month. Temperature this month, and that will change, and the current grain height and the current number of deer in the population. Here are some quantities. Use these. This is how much things happen per month. Okay, the grain grows a certain amount, the deer eat a certain amount, and so on. We're going to do this with sections. Okay, so we talked about pragma OMP, parallel sections, and then pragma OMP section, and then each one of these gets spun off on its own thread. You're going to have a deer function, you're going to have a grain function, you're going to have a watcher function, and the watcher function, well, watches over everything. It also will increment the month, possibly increment the year. It will determine temperature and precipitation based on what month it is. And you are required to come up with your own agent. Your agent can be almost anything, but it has to somehow interact with the simulation. Okay? Don't, your agent cannot be, I'm just trying to make something up. Your agent cannot be what the temperature is in another country. Okay, from whatever this one is. Okay, it has to interact somehow. It could be zombies from outer space. I don't really care. It doesn't have to be realistic, but it has to somehow in your storyline have an interaction with grain or deer, or preferably both. Okay, and then when you graph it, we're going to see that. That's how we're going to know that your agent actually worked, is we're going to look at the graph and go, oh, look, these zombies from outer space go up and the deer population immediately go down, or however your storyline works. So when you start the whole project, start the whole project without the agent, which means this will be a 3, not a 4. Okay, just get the first part running, but eventually you're going to add a fourth one. You're going to change this to 4. If you want to do the seed for the random number function, yeah, put that in too. The temperature and precipitation are a function of a particular month. So January is 0 and so on. This will give you some numbers. Yeah, go ahead and use it. I put it in a function because you want to call it once at the start of the program, and then you also want to call it each month at the from the watcher thread. Okay, starting values. Yep, we're starting in January 2024. Yeah, let's start with 2 deer and 5 inches of grain, and we'll go from there. So this is what we talked about when we talked about functional decomposition. Okay, let's say that we have 2 quantities, and this works well in our case because this could be deer and this could be grain, and the watcher thread. Okay, we've got 3 barriers. So here at the start of the function, so there's a while loop in the function, but at the start of the while loop, deer are going to look at the whole environment, the whole state, temperature, precipitation, which they're not going to use, inches of grain, and possibly your own quantity, and decide what the deer population does in the next month. Okay, it can't write that back out to the state because it doesn't know if the other threads are done using the state. Okay, that's what this first barrier is for. That says we are all done using the state. We've computed our next values. So when they all get to the barrier, then they can go on. And right now, after that barrier, they're going to copy their next values back into the state. And then there's another barrier because they don't know when the other quantities are done copying back to the state. Okay, but once you get past this second barrier, now the state has been updated. Now the watcher thread has something to do. So it really doesn't have anything to do here, nothing to do here. Now it's going to print out results, the new state. It's going to look at or it's going to bump the current month. It may bump the current year. It's going to calculate new temperature and new precipitation. And everybody's waiting at this barrier because we don't want to let the quantities go back up to the top until we're sure the watcher is done using the quantities. Okay, so you typically do this sort of thing with 3 barriers. First barrier says, I've computed my next quantity. What happens to me in the next month? Second barrier is, okay, I'm done copying to the state. And then the third barrier is the watcher's done doing whatever it does. So yes, you have to make that happen. Okay, quantity interaction. Again, I've just sort of made up some functions here just to make the whole thing work. And again, here's more logic about figuring out how much the grain grows and what the deer population does. Yeah, make sure you don't go negative on the number of deer. That's not possible. Each of those 3 functions, deer, grain, watcher, and the fourth one, your own agent, are going to be structured like this. They'll all be structured exactly the same. There will be a while loop. While the current year is less than 2030. The watcher's job is to increment the month, and if the month goes beyond 11, set the month to 0 and increment the year. So eventually the year will get to 2030, and at that point, each one of these functions will end and return to the main program. That is, the thread will exit. Okay, so while this year, here is the first thing. to do, compute the next month, wait at the barrier, copy to the state in here, wait at the barrier, or wait for the watcher to do the printing, wait at a barrier, and then continue on with the while loop. Okay, now we talked about barriers in OpenMP, Pragma OMP barrier, but we can't use them here because the OpenMP specification says all threads must execute the barrier region. Well, in English, what that means is all threads have to be waiting at this or have to encounter the barrier at the same memory address, which we're not going to do because we have 3 different functions or 4 different functions. And so they are all want to wait for a barrier at a different memory address, okay? Because they're each in a different function. No problem. We're just going to write our own. So there's a function called a init barrier, which you're going to set up. And this is how many things you're going to wait for at the barrier. You need to set up some global variables. Here's what a init barrier looks like. Just copy and paste. And here's what wait barrier looks like. Just copy and paste. Basically, what this is doing is it's counting. Okay, instead of injecting code at a certain memory address, which I think is what OpenMP wants to do, it's just going to count. And so you tell it in a init barrier how many you're expecting. And the moment that number of threads arrive at calling this function, then you're going to release the barrier. So yes, this seems to work. Okay, yeah. So what you're going to do, again, you don't do performance in this one, but you do results, and you're going to have 72 months worth of values, which you will graph. The graph will, well, you'll have a table first, which will show temperature, precipitation, deer, height of grain, and your zombies from outer space or whatever. And you'll make a graph out of that table, okay? And then a commentary. What patterns do you see in the graph? So when I did it, this is what I got. The green is the height of the grain. The blue is precipitation, which is fairly periodic because that's what the function here in the notes is doing. Temperature, also somewhat periodic, but out of phase with the precipitation. And when the when the temperature and precipitation are low, the grain stops growing, which means the deer population diminishes. But now the temperature and precipitation are higher and there's less deer munching on the grain. So the grain goes up. Basically, anything of this kind of simulation is very much sort of cyclic, but the cycles are out of phase. Is they're each reacting to what each other had done like the previous month. So yours will look different from mine. Plus, you'll have another agent. You'll have another quantity in there. So you'll actually be graphing 5 different things. Okay, and here's the rubric. Make the simulation work. Add your own quantity. Do a table of numbers. Yeah, I know it'll be 72. Just interesting for us to see your actual numbers. Draw the graph, and there's only one graph here, not 2, not 3. And tell us why it looks the way it looks. Okay? Well, no. Yeah, but run it without your own agent first. Make sure that your graph looks something plausible before you add your own agent, and then you can see what the effect of the agent is. So this is functional programming, and a lot of things can be done this way. So have a good time with this.